Good morning, welcome back. Hello. Hi. Everyone's asleep. It's too early on a Friday morning. Let's just jump right in. We're doing two sections again today. We're going to look at similar triangles, going to be very similar to last section, similar polygons. And then in similar triangles, we're going to talk about some parallel lines and proportional parts. So let's go ahead and just jump right on into similar triangles. This is section 7.3. So in order to identify similar triangles, it suggests that two triangles are similar if they've got two pair of corresponding angles congruent. And so that's our first big postulate today. If two angles of one triangle are congruent to two angles, let me spell angles, not angels, to two angles of another triangle, then the triangles are similar. So if you're trying to show that you've got some similar triangles, you do not need to show that the sides are proportional. Last time in class, we were talking about proportional, similar polygons. We had to show all the angles were congruent, and then we had to show that all of the sides were in proportion. Well, in this case, with this postulate behind us, we only have to show that the angles, two of them, are congruent. Question is, why only two? Only two because with the third angle theorem, we get the third side for free. Why not the sides? Well, when we were talking triangles back in chapter 4, we had this Hinge Theorem thing that allowed us to look at these side lengths in triangles based off of comparing their angles. Which angle was bigger than the other meant that the side across from it was bigger than the other side. And so putting those two things together, it kind of gives us enough information to make this postulate work without too much of a proof. Okay, so we're just going to be like, okay, if we've got this set up, then we can say these triangles are similar. So I'm going to go ahead and write down the name of these triangles. This is triangle ABC. Here's the symbol for similar. And now I need to write the name of the other triangle. But remember, order matters. So I have to find the corresponding angles. A has two arcs in the angle. If I look at the other triangle, E has two arcs. And so A corresponds to E. And since A was written first, I have to write E first in the second triangle name. Next up was written B. It has one arc, so I'm going to look in the second triangle. I'm going to find the one arc angle, that's F, so F gets written next. And then finally D. Okay, super, super important that you make sure that you put these things in the correct order. The first name, I don't care what order. The second name is based on the first shape's order. Let's determine whether these triangles are similar or not. I'm going to pop into the homework real quick. Excuse me. I'm going to pop into the homework really quick, and this looks like it's questions 1 through 4. So I'm going to write up here that this example 1 is going to walk you through skill practice, section 7.3, questions 1 through 4. All right, determine if they're similar. If they are, write the similarity statements, explain your reason. All right, going to look at this, and I'm going to get some color going here. I see that this triangle L, this point L has an angle measure 57. And if I look over here, I see M with an angle measure 57. Those two are congruent, so I'm going to call them corresponding. Now, angle J has a measure of 48, but angle P doesn't. Now, my third point is missing a letter, so let's just name it anything we want. I guess we'll name it N. So it's NMP. Okay. I don't know what this angle measure here is at N. And I don't know what this measure angle is here at K. So I'm going to go ahead and find one of the angle measures using the third angles theorem. Third angles theorem said if I add up all the angles in a triangle, I'm going to get to 180. So I'm going to take 180. I'm going to subtract off those two angle measures that I have here. I'm writing it, which means I don't have hands to get to my calculator. So someone with a calculator, please, 180 minus 48 minus 57, yell at me what that is. Someone, it's 75, okay. Hey, that looks like that's the same measure as P. So I'm gonna go ahead and I'm gonna say that K and P are corresponding. I don't know yet if the triangle is congruent. Wait a minute. I can use this postulate. I have two pairs of angles that are congruent now, yes? Yes, which means I can immediately state these triangles are similar and I don't need to do anything else. So I'm gonna go ahead and type my thing. Triangle LJK is similar to triangle, I have to put things in the right order, MPN, because postulate 7.1, two angles are congruent. Okay, let's make this fit my space a little bit better. There you go. And that's how you're going to do questions 1 through 4. Any questions on this? Yep. Ooh, great question. Like here on angle does B? Yeah, let's look at B next. So the question was, in case you couldn't hear, repeating this for the recording, how would we do this without angle measures listed? All right, let's look at B and let's try to dissect what we already know. I see two lines, RW and ST, intersecting at S. Whenever I have this set up, I've created some vertical angles. And those vertical angles are here and here, and they're also on the unmarked portions here and here. If I think back, way back, like chapter 2 or 3, something like that, we had this statement that said that vertical angles were congruent. So I have right now the angles here at S are congruent. So I'm going to go ahead and write that in. I've got angle RSX, that's the angle that's facing to the left, congruent to angle WST, that's the angle to the right. And I put them in this order to try to force R to be corresponding to W. All right, the next thing that I'm going to look for is anything else that could help me get some congruent angles. And I noticed that I've got some parallel lines happening right here. This line XR and this line WT, those two are parallel to each other. They have the little parallel line marker, the little extra arrow thing happening. Okay, well, since they're parallel, that means that one of these lines, either one that we want to look at, are a transversal. So I'm going to take a moment, I'm going to highlight that a little bit. Let me make my highlight line a little thinner here. So this line and this line are the parallel ones. And my transversal, we'll look at RW as the transversal. So if I ignore everything else and I look at just the blue and green lines, I notice that right here and right here, I have alternate interior angles. Back to chapter 3 things. So that means this angle sitting here at R and this angle sitting here at W are congruent by the alternate interior angle theorem. And that came to us from chapter 3, I think. And don't need you guys to have this memorized, but be thinking through these kinds of setups and go, ooh, where have I seen this before? Go back into your notes. You should have them printed. Flip around until you find something that looks similar to it, like I have here on my little review sheet. find something that looks similar to it and go, okay, let me read a little bit more on this and see what it says. By doing that over and over and over again, getting some practice doing that, you'll get these closer to memorized. All right, now that I have two angles congruent, the triangles are similar, aren't they? Yeah, so we got to name these. So R and W are corresponding, and the S's are corresponding. So I'm going to go RSX and WST. RSX. Similar to triangle TSW, and my reason is postulate 1.7. Awesome. Thank you for that wonderful question that led me to my second example for the day. Yes, ma'am. Yes. Any other questions? I'm looking around the room for hands. I'm looking in my chats. All right, so far so good. All right, I'm gonna go ahead and slide on down to our theorems for the day. We've got some theorems regarding triangle similarity, and these names are gonna look really, really familiar. The side similarity. Looks familiar? It says, if the corresponding side lengths of two triangles are congruent, or excuse me, are proportional, then the triangles are similar. So if I'm trying to show that triangles are similar, but I only know information about the side lengths, what you want to do is set them up in some sort of proportion. And if you can get those fractions to be equal to each other, then we can say that the triangles are indeed similar. I'm going to do an example of that here on this one. Let me scroll down to 2A. This one right here. So I've got two triangles, want to know if they're proportional to each other or not. And so what I'm going to do is I'm going to try to find some corresponding sides. Now I don't have angles to tell me which corners are corresponding, but I can see that this side right here is the shortest side in this triangle. So I'm going to set it corresponding to the shortest side in the other triangle. And I'm going to do that all the way around with all of my sides, matching up the shortest with the shortest, and the longest with the longest, and the medium with the medium. And now all I have to do is just make fractions out of all of these numbers and hope that the fractions are going to be equal. So I'm going to do the pink sides first, and I'm going to do the triangle on the left over the triangle on the right. Okay, I can reduce this fraction down, both things divisible by 4, so I get 4/3. Okay, gonna do the small sides, gonna do the triangle on the left over the triangle on the right. 8 divided by 6, both are even, both are divisible by 2. 8 divided by 2 is 4. 6 divided by 2 is 3. So far, so good with trying to get those fractions to be the same. I only have one pair left to do, and that's the yellow side. So triangle on the left divided by triangle on the right, that's 12/9. 12 and 9, both divisible by 3. 12 divided by 3 is 4. 9 divided by 3 is 3. All of my fractions are identical. That means all of my sides are in proportion with each other. And so these two triangles are similar by that 7-2 postulate, the side similarity. Questions? Was that all right? let's take a look at the second theorem that we had, which was theorem 3.3. Theorem 3.3 is the side angle side similarity. And this one says if the lengths of two sides of two triangles are proportional and the measures of the included angle are congruent, then the triangles are similar. So for this one, we need proportional sides. So this side should be able to create a fraction with, say, this side. And this side should be able to create a proportion with this side, and that those fractions are the same. And the included angle needs to be congruent. That is the angle that's created by those two pairs of sides. Okay, so this should look really, really, really similar to the side angle side congruence. All right, let's run an example on that. I want to do example A. All right, we want two pairs of sides to be in proportion. That means they have the same fraction. And we want a congruent angle. I'm going to grab the congruent angle first because I see some sides intersecting. Because these sides are intersecting, I've got some vertical angles here and here, and so those angles are congruent. That tells me which sides I need to have fractions for. I need to have that one and that one, and this one and this one, because those are the ones that come together and form those angles. It gives us the included angle. All right, I'm going to grab some proportions, going to do the triangle on the top divided by the triangle on the bottom. I've got a decimal in my fraction. I don't want to try to reduce that in my head the way I did the other ones. So I'm going to turn that ratio into a decimal. I'm just going to do 5 divided by 12.5 in my calculator. I found my calculator. There it is, 0.4. We're happy. Going to do, bless you, the next triangle. Triangle on the top's information divided by triangle on the bottom's information. Again, I'm going to go to my calculator to give me a decimal. And when I do that, I see that it's 0.4. Because the triangles have an included angle, because I have the included angles congruent and the two pairs of sides in proportion, that is, the ratios are equal, these two triangles, please name them. Triangle PQR, might as well go ahead and name them while I'm here. Triangle PQR is similar to triangle SRT. And this is theorem 7.3, side angle side similarity. I do recommend when you're doing these practice on the homework that you write out the theorem number and the theorem name. You write out the reason why you're using those theorems, because that's your practice to knowing how to apply these theorems, especially if I hand you a proof and I say, prove these triangles are similar. Let's look into the homework to see which questions this will help with. Yeah, probably still numbers 1 through 4. This continues 1 through 4. Yo, I can't write. Questions? Looking in the chat, looking around the room. Everyone has fallen asleep on a Friday morning. Sorry, I'm so boring. Okay, I got a few, like half chuckles. Last up is once you can show that triangles are similar, you get some properties. And these properties, super familiar from before. We've got the reflexive property that says that a triangle is going to be similar to itself. We have the symmetric property that says if you've written your similarity statement in one direction, you can write it in the other, and you can swap the positions across the similarity statement and not change anything. And then the transitive property, which says if you've got one triangle showing similar to some other second triangle, and that second triangle is similar to some other third triangle, then the first and the third triangles are similar to each other. This should not be any huge surprise because we've handled transitive property pretty much the entire year. I'm going to glance really quick into here. So here we need to identify the similar triangles and then find the measures. So this is combining what you did in the first section with some algebra. Let's look over the parts of similar triangles. All right, so as we look at this, let's identify our similar triangles. I see that A, this corner A, is being shared by the small triangle, triangle ABE, and it's being shared with the bigger triangle, angle ACD, which means A is congruent to itself. That's reflexive property. I've got some parallel lines back from chapter, I think it was 3 with parallel lines and transversals. These corresponding angles are going to be congruent. So angle B and C are congruent. Okay, I know that my triangle ABE, the small one, is similar to ACD, the big one. That means that our sides are going to be in proportion. All right, going to get some highlighting going on. Yes, sir. Okay. BE is this length right here, so we're going to need to find the value of X. So let me do that first. This side corresponds to this side in my big triangle. All right, so I can write that in a proportion. So I've got the small triangle divided by the corresponding side in the big triangle. All right, there's one fraction. I'm writing it as a proportion, so I need to write it equal to. And now I need to write some other sides that's helpful to me. If I look at the side here between A and E, that's not helpful right now because there's another variable in there, Y. That doesn't help. So I'm going to look at the side between A and B. That side from A to B corresponds to the side A to C on the big triangle. And I have links for both of those, and I don't have any variables on those. So that's going to be the easy one for me to write. So on this fraction, I did the small triangle on top. So for this fraction, I'm going to put the small triangle on top. And this looks familiar from last class session, yes? It's a proportion, cross multiply and solve. Five x equals whatever 3 times 3.5 is. I'm grabbing my calculator because I don't know what that is. My calculator says it's 10.5. I'm going to divide both sides by 5. And my calculator tells me is 2.1. X was the measure of BE, and so I have found the measure of BE. We're going to do the same idea to find the measure of y. I want to do just the setup for you, and then we'll move into the next section. Here is where y is on the small triangle AE. And then here is the big triangle that corresponds to that, A to D. All right, so AE is y. I'm going to put that in the top of the fraction. And now I need to do AD. I don't have a length for AD, but I know that it's whatever I get for AE plus this piece over here on ED. So that's y plus 3. That's going in my denominator. There's the fraction of those two sides. I need to write that in proportion. I'm going to write that equal to. And now I can do either this, the yellow sides, or the blue sides. I'm going to pick the blue sides because the yellow sides have decimals, and decimals kind of freak me out. So I'm going to put the small triangle information on the top, the big triangle information on the bottom. And once again, I have something that looks really familiar to me, something that I can cross multiply and solve. So there's 5y, and this I need to multiply the 3 to the y plus 3. Okay. As I solve this out the rest of the way and just kind of quickly show my work, I'm going to field any questions you have, either live audience, raise your hand, speak up, or use the chat, the live chat in Zoom. Here, lovely conversation going on in the far corner. That is fantastic. I hope that's helping you guys out. But if it's not helping and it's off topic, you'll probably want to save it for later. All right, questions? We're okay with this? I'm looking around the room. I don't see any questions and nothing's come up in chat, so I'm going to assume that this feels okay. And I got a thumbs up from across the room. Thank you. Let me take a look into my homework. Yep, that's definitely 5 through 8. So going to go ahead and write here next to example 4. Example 4 will help you with skill practice. Questions number 5 through 8. 9 and 10 are thinking ones. Go ahead and take some time to chew on those on your own. Let's hop into the very last section, 7-4. 7-4 is called parallel lines and proportional parts. You already got a hint of that in the last example that we did. And so let's kick it off with our first theorem, which basically comes from the work that we did in that previous question. It says, if a line is parallel to one side of a triangle and intersects the other two sides of that triangle, then the line divides the sides into segments of proportional lengths. We basically use this theorem already without giving it a fancy name, but now we have the name for the theorem in case we have to write a proof with all that algebra work showing that x was a specific value. This is using the same idea. Okay, so we'll do this example super fast. All right, says in the triangle PQR, line ST is parallel to line RQ. If the measure of PT is 7.5, TQ is 3, and SR is 2.5, find PS. Okay, we've got a lot going on. I put colors on everything. Let's go ahead and find where things are. Here's PT, here's TQ, which means that from P to Q is whatever we get when we add PT, the yellow, to TQ, the green. So 7.5 plus 3. All right, let's find where SR and PS is. SR is here, 2.5, and we're trying to find PS, which is, I don't know, so I'm going to make that my variable. I'll call this X. Okay, we can figure out P to R. P to R is whatever I get when I add PS to SR. You know what? This theorem allows me to shortcut. This, I would have a really weird fraction with this crazy little expression sitting in there, and maybe it would make things harder than it needs to be. So instead, I'm going to use this theorem. It says that the line divides the segments into proportional lengths. This piece and this piece as a fraction is equal to the measure of this piece and this piece as a fraction. Which means the measure of this yellow piece divided by the measure of the green piece as a fraction is equal to the pink piece, because that's the longer of these two, and the yellow was the longer of those two, and I put the yellow on top. There we go. So now I'm just going to fill things in, and I didn't even need this information. Oh, waste of brain power. All right, there is PT, there's TQ, there's SR, and I'm going to put my variable here. That's what I'm trying to solve for. And once again, we're back to solving proportions, cross multiply and solve. I'm using my calculator to help me figure out what 7.5 times 2.5 is. My calculator tells me that it's 18.75. That's equal to 3x. Some of you can probably figure out this multiplication and division stuff very quickly in your head by just grabbing your calculator, multiplying and dividing really fast, and can spit out an answer. I'm super glad that you can do that. I still want you to go to the very tedious process of identifying what you're cross multiplying by, because algebra 2, calculus, and all of those are going to come along, and they're going to have you do this exact same thing. But I'm telling you, these fractions, they stop having just like 1 or 2 letters, and it's like it's all letters, and it looks hard, but the process is the same: cross multiply, solve. Questions? All right, but we can make this seem more complicated, and it's not. The way we make it seem more complicated is by taking the converse of the thing that we just did, which is if a line intersects two sides of a triangle and makes them proportional, then the line is parallel to the third side of the triangle. Where the first one is useful when you know that that line is parallel and you're trying to calculate information, this one is useful when you have the information to calculate with and you're trying to state that the lines are parallel. Again, this one, super, super useful when you're writing proofs. Example 2 asks you to determine if lines are parallel. It's using this particular theorem. All right, let's check if these lines are parallel or not. I'm going to grab my highlighter. In triangle DEF, here it is. The line E to H is 3, so I'm going to highlight that blue. HF 9, so that part is 9. Yellow. DG is 1/3 of GH. Okay, let's write that as a little equation. DG is 1/3 GF. Okay, here's DG. GF is what I don't know. All right. I know that the blue and green are in a fraction together and the yellow and red are in a fraction together. So I'm going to go ahead and set up my fractions over here, and I'm going to get some color going so we can see what's going on. All right, there's yellow, which goes with red. And then blue goes with green. Blue is the smaller of the two. On the left fraction, I put the small one on the top. So here on the right fraction, I'm going to put the small one on the top. There's my color coordination, and I'm going to fill in what I know. DG is the yellow. This is the information I need to put here in the yellow. And all of a sudden, you guys are freaking out because I have a fraction sitting inside of another fraction. Calm down. We'll show you how to fix it in a second. Let's go ahead and fill in the rest of our information. Just filling stuff in based on my color coding. This is where all of your practice with the cross multiply and solve comes in. I'm multiplying those two together. 1/3 x times 9. And that's all I'm going to write. I'm not going to worry about how to do that just yet. I'm just making notes for myself. The next one is x times 3, which I can write as 3x. All right, now I'm going to figure out this thing on the left. I've got a bunch of numbers multiplying together with a letter. So I'm going to stick that letter at the end. And now I'm going to think about 1/3 times 9. I'm going to do that work way over here so that I can think about it. 1/3 times 9. Now it feels like multiplying fractions with whole numbers is hard to think about, but you can think about whole numbers as fractions. But why more fractions? Because fractions are easy to multiply. Just go straight across. Just go straight across. 1 times 9 is 9. 3 times 1 is 3. And so that says 9 divided by 3 times x. Well, 9 divided by 3 is 3. Okay, if I were to divide both sides by 3, I get something weird like x equals x. Wait a minute, this really does work out. This really does work out. Here's the reason why. That's telling us that whatever this fraction is, it's the same as this fraction. These things are proportional. Yes. Yes, these lines are parallel. Right? We were just trying to see that these as a fraction are equal. And because we got to something that are equal, yeah, those fractions were equal. I'm going to glance into the homework real quick. Here we go. That's 3 through 5. This section right here, 3 through 5. This top part up here, 1 through 4. Questions so far? There might be an easier way to handle this. I encourage you to find it. All right, let's talk mid-segment. We talked about this in trapezoids. We had the mid-segment of the trapezoid, and there was a little note off to the side over here that I did not do a really good job of pointing out back in chapter 6. And I had a couple questions come up as people were taking the quiz, because the quiz called the mid-segment the median. So this is basically the median of a triangle, the median of a trapezoid. The median, this mid-segment of the triangle, is kind of this special case scenario, and it's very similar to that trapezoid mid-segment theorem that we saw last chapter. It says a mid-segment of a triangle, mid-segment being the same as a median, it's going to be parallel to the third side of the triangle. Kind of like the mid-segment was parallel to the bases of the trapezoid. And it is half of its length. Ooh, cannot spell. All right, let me get this so that way we can read it. There we are. So we get a formula. We get a formula here that says this line segment JK, the mid-segment, is 1/2 of that base of the triangle. And this should feel almost identical to the mid-segment. We just don't have any things to add because there's only one base here. If this were a trapezoid and H had like a length here, then we'd add this length to this length and divide by 2. I feel really comfortable that most of you can parse this out. You're just using this theorem. The only part that makes this hard is the diagrams now look like this, and color code to figure out which mid-segment goes with which base. So this mid-segment goes with this base. This mid-segment goes with this base. Questions? We're okay with that? Yep, got some nods. Good, everyone's awake. That's going to help you with 6 through 8. Now that mid-segment thing and everything we've talked about so far gives us 2 corollaries. Corollaries are things that fall out of and are the result of some previous theorems and postulates. The first corollary says this: if 3 or more parallel lines intersect 2 transversals, I'll fix that in a second, then they cut the transversals proportionally. What? Parallel lines, here they are. They've got the little arrow markings. The lines that are intersecting those are the transversals. They're going to cut them into proportional pieces. So this piece here is going to be in proportion to this piece here. And this piece here is going to be in proportion to this piece here. And then this entire thing, the pink and the blue, is going to be in proportion to this piece, the pink and the blue. And all the proportional games that we've been playing so far, you can play with these. One last corollary and then a new example. The second corollary that we have is if parallel lines cut off congruent segments on a single transversal, Then they're going to cut off congruent segments on every transversal. So if this piece here is congruent to this piece here, then this piece over here is going to be congruent to this piece over here. With that, we can do some algebra. We'll do that as our final example. That's going to help us with number 9 through 10. So going to make a quick note here. This covers 9 through 10. All right, I'm going to find X only, and then we'll cut this off and you guys can find Y on your own. Taking a look here, I see that this piece is congruent to this piece, which means it's really easy for me to find Y, set those two equals to each other, solve. But this corollary lets me say that these two pieces are congruent to each other also. So I'm going to set those congruent and solve for X. While I work this out, just going to check to see if we've got any questions. Live studio audience, go ahead and shout out those questions to me now. Right meow, or use the chat. No questions? All right, that's all we had for you today. Thank you very much for joining us. If you're watching this on YouTube after class, please don't forget to like and subscribe. And if you're in my class this year, hit the bell, the notification. That'll tell you when I've got this particular video uploaded. We usually happen sometime after class. So have that notifications. That way, when you're stuck at home, you know exactly where to go to get some help and to rewatch your examples. Don't forget, give me comments in the comment section, catching up on those, and give me a timestamp. Let me know when I ran these examples for you if they helped. Thanks. Have a good one. We'll see you later. Bye, guys.